you to come out of this session with an understanding of what a hierarchical model is and why it might be useful for your research going forward. Hierarchical Bayesian modeling is really quite jargony, and it in and of itself is not very complicated. There's really just like one main concept that if you get that, you'll understand what it is that we're doing. It's one of these things that you have to be kind of pragmatic over it. Like sometimes it's really useful to create a hierarchical Bayesian model, but sometimes it's too much computation time for what it's worth. Like sometimes you actually you don't really need to use it. But it is something that it's kind of ubiquitous. Like you can turn any inference problem into a hierarchical problem. Often we don't because it's computationally intensive and not necessarily needed. Okay, so you've covered probabilistic graphical models already this week, right? Okay. Oh, do you wanna? Oh, it's okay. So the easiest way to kind of describe what a hierarchical model is, and I think this is a PGM that looks like a hierarchical model to me, but so you might already have come across them, either this week or previously in your research. So okay, so basically when we're drawing a probabilistic graphical model, we're trying to lay out the conditional dependencies of all of the elements of the inference problem. So you have some data, which is observed. Oh, this is too big. I need to work on my Blackboard practice. Okay, so you have some data that's observed. You have some model parameters that you want to constrain. And then this typically will have some prior distribution. To make this hierarchical, the only thing that changes is that this becomes an open circle, and you have some parameters, alpha, say, of your prior that you're now going to infer. So the difference between a hierarchical model and a non-hierarchical model is just whether you fix the prior or whether you infer the prior. That's one way to think of what a hierarchical model is. And so you can now kind of see that any problem that you can think of, you can probably turn it into a hierarchical problem. There's one more thing that we probably need in this scenario, though, which is a plate over the data and the parameters. Because if we're going to try and infer the prior distribution over our model parameters, then we probably need a large amount of data. And I'll kind of get into that a little bit more. But so what this kind of means is we have priors which define the distribution, the probability distribution of our model parameters. And so if our model parameters are drawn from a distribution, then we need to have observations from each of those model parameters, which means usually we have like a family of observations, a group of observations. So hierarchical modeling, you can think of it as where you're learning about some underlying. In fact, I have a quote on my slides. Okay, so it's where you learn about some underlying population or an individual using a group of individuals. So you might have, say, you might have a group of stars, and you want to learn something about each of those stars. And You can learn the properties of each of those stars better if you use all the stars than you can if you just use one star. So and again, this is related to the prior, right? So if you have a star, you want to know something about one star, you have some model parameters, maybe you have its age and its mass as model parameters, and you have some observables like its luminosity and its temperature, and you want to know the age and mass of the star. You might have a prior over age and mass. Your priors might be star formation history for the age prior and an initial mass function for the mass prior. And so you can get an idea of what the age and mass is of that single star by fitting that model. But if you have a group of stars, you can learn from the group what the star formation history is and what the IMF is, and use those as your priors. And you'll get a better answer for the age and mass of your single star. So hierarchical modeling, as I said before, isn't always the right thing to do. It might be that actually you can get a pretty good guess of what the star formation history and the IMF is, and it doesn't actually make that much of a difference to your single star. Or it might be that actually fitting for the ages and masses of each star individually and then combining them at the end might be pragmatically the better thing to do in terms of computation. And so what I kind of mean by that is any time where we have a group, a population of objects like stars, and we make a histogram over the properties of the stars. Say you have a group of stars and you measure the ages of all those stars and you make a histogram over the ages of those stars, you've kind of separated what could be a hierarchical problem down into two stages. The hierarchical version would be not to draw a histogram, but to parameterize the histogram. Say it's a Gaussian. Instead of measuring mu and sigma from the histogram, you'd say mu and sigma are parameters in my model that I want to infer. And so you do the whole thing at once. Okay. So maybe we should go through a few examples so that you kind of have maybe a better sense of where and when you'd use it. Okay, so one example would be, I'm using the Hubble constant as an example, but I know nothing about cosmology, so I might say some things that are wrong, but that's okay. You'll get the gist. So, okay, there's this tension over the true value of H naught. That we get one value from supernovae, we get a slightly different value from Cepheids, we get a slightly different value from tip of the red giant branch stars, and a different value from CMB power spectrum. And what you can do with all of those different values of H naught is you can write them all down, or people often draw like values with error bars, and these are all of the different measurements of H naught. And then people will look at this and they'll say, what do we believe about H naught? If you believe that all of these measurements of H naught are valid, though, and maybe they are just the same measurement of H naught with some noise, then you could infer an overall H naught from all of the H naughts and all of the observations of supernovae, Cepheids, etc. at the same time. And then you'd infer a sort of mean value of H naught, and that is your prior that you're inferring. And you'd infer a standard deviation for that distribution of H naughts. So I can draw this as a PGM. Okay, say you have your supernovae measurements of distance versus velocity, and you have a version of this for Cepheids, a version of this for tip of the red giant branch, and then you have your CMB power spectrum, which looks slightly different, but it's still data and model. Then what you would have is your observations, your distances, your V's for supernovae, here the subscript is for supernova. And you'd have some measurement. Oh, sorry, let's actually. Some measurement of H0 from supernovae. And then this would have some, in the non-hierarchical version, right, this would have some prior parameters that are fixed. But we don't want to do that. We want to infer the overall H0. So we need to add in, this is going to be a plate over n supernovae. So we can do the same thing for Cepheids. And we want to infer an H0 from the Cepheids. This is also going to have some noise, sigma bs, which is the uncertainties of the velocities. This has some noise. And this is a sum over Cepheids. And this has some prior, that in the non-hierarchical version is fixed. And so you'll end up with these two different measurements of H0. But if you want to combine those measurements and say these measurements are the same measurement, they're just drawn, it's just that H0 is observed with some noise. Then what you want to do here is say, I believe that there is some mean value of H0 and some standard deviation for the distribution of H0s. And you want to infer these from these. So now it's hierarchical. Did you go over in the probabilistic graphical model tutorial how to write down the factorization, the conditional probabilities from? Okay. Okay, so this is like a, I guess, kind of fairly simple, fairly standard version of a hierarchical model where you're going from a sort of non-hierarchical version and you're just turning this prior into an open circle and you're inferring the parameters. But you can imagine going hierarchical in a different direction, which would be instead to say that there's another layer below this, because where did we get these velocity and distance measurements from? We got them from some, say again? Exactly. We got them from some telescopes. These are measurements that we've made from the data. So we've already done an inference process to get here. These are not raw data. These are posterior distributions over velocities. So we can add a hierarchical layer if we wanted by adding down here like the flux and the wavelengths of some spectrum that we've measured from our supernovae. I don't actually know how you measure velocities of supernovae, but presumably it's something like this. Okay, so there are kind of many ways in which we could make this model hierarchical, and you can keep going down until you get to the raw data, but it's not always pragmatic. Like, it's not always going to improve your inference. The way it will improve your inference is if you need support from all of these observations to get a precise constraint on these things. If you need to, learn from all of the family of the observations. That's when you go hierarchical. And we'll go through an example where we do exactly that in a second. Okay. Yeah, so this, the simplest HBM, that's just kind of this picture of what I drew at the very start, like data, model parameters, and then to make it hierarchical, you just infer your prior parameters too. And as I just said, most problems in astronomy, like pretty much any problem that you can think of, any problem that you have worked on or will work on that's an inference problem, you could have made it hierarchical in some way. Yes?
Okay, so in this example you just gave of trying to fit a prior to the H-naughts, you could imagine that some of those observations might implicitly, and I'm not going to step on any feet by like saying which ones or whatever, might be more precise and have smaller error bars. So if you're fitting a single sigma to the whole thing, like could those lower level hierarchical levels help you propagate errors up and figure out which ones might have more or less error bars if you did it in like a deeper.
So I think okay, so you're asking if in this hierarchical model can that teach you about which of your measurements are trustworthy and which aren't? It depends on how you set the problem up. So if you say like I actually think that probably both of these measurements of H0 are wrong by some amount that I mean, that's kind of what the standard deviation parameter is doing there for you. But if you believe that there's some other inconsistency, like maybe the error bars are wrong, the error bars on the velocities are wrong, then you'd have to include that in your model if you wanted to infer that. But you could. But there is an implicit assumption here, which is that the prior is a Gaussian with a mean and standard deviation. And by writing the model down this way, that is our assumption. And so we will find, when we fit it, we will find that that is what we get, because we constrain the model to be that way. So if that's not a valid assumption, then this is the wrong way to go. There are definitely so the other thing that might happen is like your model might be wrong. So in the example I gave for stellar ages, something that I'm working on, which is a hierarchical problem right now with Rocio Kieman, she's been around this week, is where you have okay, stellar ages are really difficult to measure, and so if you combine different observables of stellar ages, you can actually constrain age much better. And so if you use, say, a rotation period for a star and its position on the HR diagram and its abundances and its velocity, these are all age indicators. So we can use observables of all of these things to infer ages for our stars. But that only works if the models are right. So if the model for how the rotation period of a star changes over time is wrong, we shouldn't include it, right? Because it will inform age, but it's wrong. So it will mess up the ages. So what we're doing in this model is we have all of the parameters of the models, the age models, are free. So they are hierarchical parameters in this scenario. So the relationship between rotation period and age is a power law, and the index of that power law is a free parameter that we infer. And it's just one, it's the same for every star. There's one power law index. And so we're inferring the ages of a whole bunch of stars, so like thousands of stars, so we're inferring thousands of ages all at the same time, and we're using those ages to calibrate all of the relationships between age and observables at the same time. And that's, again, that's an example of a hierarchical model that you can't do that any other way, really. You kind of have to use this approach because we don't know the ages of our stars. If we knew the ages of our stars a priori and we could measure their rotation periods and their abundances, etc., we could just calibrate the age relations, but we don't know their ages because ages are really difficult to measure. So we've got to do it all at the same time. We have to learn about the rotation age models at the same time as inferring the ages. So if your model is wrong, you're not going to get the right answer, but that's true of everything. It's always true. Any other questions about this? Okay. Combining measurements, that's kind of what we just did. With H0, you could imagine, actually a problem that comes up quite a lot in astronomy is combining measurements because, so for example, does anyone work on like radial velocities, measuring radial velocities from spectra? For anyone? Okay, so when you get a spectrum, you often get many like spectral orders if you have a shell spectrograph. And typically what people do is they'll measure an RV, a radial velocity, from each spectral order, and then at the end, they'll take the mean, they'll take the average, and they'll say that's the radial velocity. But what you could do is infer the radial velocity from each spectral order at the same time. You say there is one true radial velocity. All of these spectral orders represent noisy measurements of that one true radial velocity. And you infer that true radial velocity, which is the mean of your prior, and the standard deviation of that Gaussian prior, which is the noise with which each radial velocity individually was measured. Another example of that would be something that I've done before is measuring stellar rotation periods using Gaussian processes, and this works best with a Gaussian process because a Gaussian process is a forward model, where I've combined observations from K2, which is a pretty precise photometry telescope, with observations from MOST, which is like a little micro telescope that has noisier photometry. And I say, okay, both of these time series are for the same star, and that star has the same rotation period. So I have one rotation period, but I want to infer it from two data sets. And these two data sets have different noise properties. They have different sigma flux. And so that's another way, again, in a hierarchical version. I could measure a rotation period from the K2 data set and a rotation period from the MOST data set and take the mean. But the more principled way to do it is just to infer one rotation period from both data sets. And in that case, I'm not giving myself too much more work to do because it's not a large increase in the number of parameters of my model. So there are lots of cases where you have many individual measurements of one thing, and you think that there's just one underlying physical process that is determining all of these things that you're measuring. And so you would just infer one of those properties rather than inferring each one at a time and then combining them at the end. Okay. And then the other example I have is this, is these are kind of like restatements of the same problems. It's all, every time it's just we're inferring the prior, the parameters of the prior, but these are kind of different like examples in the literature that you might come across. So exoplanet populations or stellar flares is another example where what we do when we try to infer the population of the exoplanet distribution, whatever, is we go to like NASA Exoplanet Archive and we download planet properties like radius and period, and then we make histograms of what the radius distribution of planets is and what the orbital period distribution of planets is. But what you could do is you could go back down to the light curve level, and you could fit the properties of the planets from the light curves, and then your radius and period distributions are your priors. And you infer, say, the mean and standard deviation of those distributions from the light curve level. That is probably overkill, because that gets pretty computationally expensive, because you have the light curves have many, many data points. If you're talking about planet populations, you want to look at thousands of light curves, and it gets pretty computationally intensive. Okay. So I think I've gone over why HBM is useful. Again, it's where you can improve your precision on the parameters that you're interested in by looking at a population. Okay, as I mentioned, there are pros and cons. The cons being that this is also often involves a lot of parameters. If you have thousands of stars and you have a parameter for each star, then it's thousands of parameters. Another way to look at a hierarchical model would be where you have per object parameters and population parameters. So in the case of the stellar ages, you have per object parameters because each star has an age, and you have population parameters because each age relation has parameters which describe the whole population. So that's another way to think about it. Okay, let's just take 5 minutes, and I want you to discuss with a partner, someone sitting next to you, is there a problem that you've worked on, maybe in your previous research, maybe something that you've thought about this week, maybe something you're working on right now that currently isn't hierarchical that you could make hierarchical? Okay, take 5. Okay, so some of the, so I've spoken to a couple of you, and there's this type of problem, I think, where that some of you are working on, where you have actually, like, you're really just interested in one system, like one astronomical object. And one way to make that hierarchical would be, instead of looking at one object, would be to look at many objects that are just like that, and learn about the distribution of properties of those objects. And in learning the distribution of properties, you will improve the measurements you make of your object of interest. Were there any, did anyone want to share anything? A model that they think would be like perfect example of something that they could make hierarchical?
As a part of my project, I have been estimating star formation rates for galaxies, and many of my galaxies don't have infrared observations. So, using traditional method, what we do is, like, we fit SED to the SED. So we fit SED template to the SED, but in that, if we use hierarchical Bayesian, then maybe we can say that, like, if you know something about the population, then the infrared observation for this kind of galaxy would lie within some region. So instead of saying that, oh, I don't know where infrared observation is, you can still apply at least some sort of constraint and maybe get better estimates.
Yeah, exactly. And so there, you'd constrain the SED of the galaxy you're interested in, and also constrain the distribution of SEDs better. Okay, so let's move on to this example. I posted a link to this GitHub repository on Slack, and it might be, I mean, I don't know that it's essential for you to run it at the same time, but it might be good for you to go and clone it right now, because the exercise is in there as well, so it'll be useful for you to have that. Okay, this problem is a worked example of a hierarchical model which uses PyMC3. I am brand new to PyMC3, so if you have questions about the details, I might point you to some other people who are more experienced with it, but I'll do my best. So the problem we're going to do is a little bit like the H0 problem, but it's just with more data. So this is like, again, we're going to fit a line because that's like the thing that we always start with in astrostats, but we're going to make this line hierarchical. Okay, so people just about got the Jupyter Notebook up and open. It doesn't matter too much for now. You can follow along just looking at the screen here. Okay. So we've got some observations Y. With given x's. They're observed with some uncertainty, sigma y. There are data points n equals 1 to n. So there are, for each one of these lines, there are n data points. N is the same for each line. And we have m lines. Oh, I probably should have chosen it's kind of hard to hear the difference between n and m. But actually, we have data points n times m. Okay, so we just have like a bunch of lines like this. They all have the same noise properties. Sigma y is the same for all of them. But the difference is that the slope and intercepts are slightly different for each line. So AM and BM, we have capital M lines. So we have capital M number of A's and B's, different slopes and different intercepts. But these slopes and intercepts are drawn from priors, from Gaussian distributions with a mean and a standard deviation. Okay, so this is a little bit like the H0 problem, but with the H0 problem, we just looked at the slope. So now if we were to add the intercept, that's kind of similar to what we're doing here. Okay. So we're going to skip over these exercises because we're short on time. So I'm just going to get straight to it. So in the non-hierarchical version of this, these priors would just be fixed. We'd have priors over our A's and B's. And we just assert that we know, a priori, that A and B are drawn from Gaussian distributions. We just know what those parameters are. But in this version, we're going to infer what those parameters are. Okay. So first of all, in this notebook, I go through how I'm simulating these data. And it's kind of useful to understand how the data are simulated because it shows us how the model is actually set up. So first of all, we want to draw A and B. Oh, I wish I could leave that up. Oh, okay. So first up, we want to draw our A's and B's from these distributions. Then we want to simulate lines from these A's and B's. So those are the two procedures in simulating the data. So that's what I'm doing here. In this first cell, I'm going to simulate 25 lines. And so I draw, and this is the true mu A, true sigma A, true mu B, true sigma B here. And I draw my true A's from these Gaussian distributions. And I draw 25 values of A, 25 values of B from these Gaussians. And then in this cell below, I'm just plotting these values of A and B. So they are drawn from Gaussians. There's only 25 of them, so it looks kind of noisy. But what we want to do is infer mu A, mu B, sigma A, and sigma B. OK, so then next step is to simulate the observations. I said n was 10. So in each one of our lines, we're going to have 10 data points observed with some noise. And so in this cell, I'm just simulating 25 lines from the 25 different A's and B's. Each line has a different A and a different B. And each line has 10 data points in it. So if I plot them all on the same axes, it looks like this. I haven't got error bars on these points because you just can't see anything if I do that. But you can see that there's a lot of uncertainty here. Like sigma y is big. So this is kind of a scenario in which actually using all of these lines is going to help us infer the parameters of just one line, because there's a lot of noise and there aren't that many data points. Okay, so let's just take the first line to begin with. This has some value of A, the intercept, and some value of B, the slope, that is drawn randomly from the prior distributions. Okay, and we're going to fit this line to the data. So this is the orange is the true line. We're going to now try and infer what the line should be from these data using PyMC3. In this case, this is a very trivial example of linear least squares. You don't need to do MCMC to fit this simple model because there's an analytic solution, but it's useful for us to just build up from from a small pared down version. It's much easier to build up from there. So the way that I would start if I was doing this, if I was coding this up, is I would start by just fitting one line to one data set. Okay, so we're going to do PyMC3. So as I said, have only just started using PyMC3 for this tutorial. So I am much more familiar with MC, and I actually think that it's really valuable to be able to do both things, because to me, I have an MC brain, and for me, writing down a hierarchical model is much easier when I can define a likelihood function. I can define a prior function. I can define a posterior function. PyMC3 for me is still taking some work. So we won't have time. We're definitely going to run out of time. But at the end of this notebook is how you would write these in MC. If we do get time, we'll go over that a little bit, but we'll see. Okay, so in PyMC3, fitting a line to data. Have you already seen PyMC3 this week? Is that right? Did you fit a line to data with PyMC3? Okay. Ooh, half of you are nodding. I'll take that as a yes, but it was probably a different model. Okay. So PyMC3, you have this. You create this model instance, and then you fill it with your things. You fill it with your priors. You fill it with your likelihood. And so that's what I'm doing here. I'm defining my priors over A and B. Remember, this is not hierarchical yet. I just have priors that I'm fixing. I'm not inferring the priors. So I have a prior over a slope, a prior over an intercept. These are uniform priors that I've decided because I want them to be pretty uninformative. I don't have a good sense of what the slope and intercept might be. So that's how I do this in PyMC3. And then the model is deterministic. Y is true Y is perfectly determined by A, B, and X. Y observed is a noisy observation. So it's not deterministic, but true Y is. What we observe is not true Y. We observe a noisy version. So this is the deterministic model. It's just the intercept, the slope. This Python indexing is just to get the shapes of my arrays right. And then this is my likelihood here. So this is Y observed. So it is a normal distribution with the mean being the deterministic model and the standard deviation being the uncertainties on the Ys. And then I didn't know PyMC did this, but it can draw the graphical model for you, which has anyone used this before? This alone might convert me to PyMC3 over MC. It's really nice to be able to, because you can check for bugs, obviously, like you using this. It's not always exactly the same as what I would expect. So there might be some gotchas in there, but I think in a general sense, it can be useful. So all I'm doing here is using this model to graph viz thing. You might not be able to run that. You might have to install something, but it's very, very easy to install. I found it very easy to install. It tells you in the error message how to install it. Okay, and then we sample from that model, make the usual diagnostic plots. We can plot the marginals over A and B. We can plot the chains. And then here are the summary statistics. So our true A for this first line was this value. And the inferred version is not very well constrained. This is the intercept. And it's not very well constrained because there's a lot of noise. Okay, so then here I'm plotting the inferred A and inferred B. The true model is the orange. The inferred one is the green. So yeah, it's like done a decent job on the slope, but the intercept isn't very precisely constrained. So let's see if using the entire group of lines, we can constrain this one line better. And my hypothesis is that we can. Okay. I do want to let's just try and get through this, I think. So what changes in the hierarchical version? It always, it takes like a little, like a second to, for me at least, to oh, okay, what are we doing? Like how does the likelihood function change? How does the prior change when we code up the hierarchical version? It's like, yeah, it's not always totally intuitive and obvious. In MC, what you would do is you'd define your likelihood function, you define your prior. In the hierarchical version, your prior just moves into your likelihood function. Now you have your prior parameters free. They're in your likelihood function. Now you have a new prior, which is your hyper prior, which is a prior over mu A, mu B, sigma B. But mu A, mu B, sigma B, they're now free parameters in your likelihood function. And it's the same in PyMC3. So let's go from the bottom up. Here, this is the likelihood of the observations. It's the same, except I don't have slices anymore in here. sorry, in y error and observed y. Before I had to slice because I was just taking the first line. Now I'm using all of the lines. One of the hardest things about hierarchical inference is data structure and organization. Suddenly you have to figure out how, with this I'm using a two-dimensional array, but I can do that because my n is the same for each line. But if I had different numbers of data points for each line, it wouldn't be so simple. So I'd have to figure out how to get all of that data into my likelihood function. That's one of the trickiest things. How many free parameters are there in the hierarchical version? There's more than 4. So there's I think 29, because I have A and B free for each line, and there's 25 lines. Plus I have 4 parameters that constrain the priors over those lines. So those are my population parameters, those 4, and my per object parameters are the A's and B's. Wait, I have 25 lines, so I have 54 free parameters. So you can see, again, you can see why I use PyMC3 and not MC. I don't even think MC would be able to converge. I mean, it would take a very, very long time to run on 54 parameters. PyMC3 can do it. It's magical. Okay, so the likelihood stays the same, but again, there's just that administrative step of getting all of the data in here now, not just the first line. The model is the same. This bit might be wrong. Now, the priors, this PyMC3 takes a little bit of work to define priors like this, but here what I'm doing is I have normal distributions with 0, mean, and a sigma of 1, and then I actually multiply those by the actual parameters of the Gaussian. I was told to do that by somebody, and I'm not totally sure why. Dan Foreman-Mackey will be around later this afternoon, so if you have questions about that, talk to him about it. He's the one who told me to do it this way. But basically what we're doing here is we're defining these Gaussian priors over A and B. But ln sigma A, I'm sampling in the log because it's a standard deviation which can't be negative. So sample in the log whenever a parameter can't be negative. Log sigma A, mu B, log sigma B, these are defined up here. So these are parameters, these are free parameters. They go into the prior here, but there's a hyperprior here over these parameters. So mu A, mu B. This top layer is where I define the hyperprior. It's just a level up from the prior where the properties of that prior are fixed. I'm not inferring them. So I have a uniform distribution as my priors. And I've just chosen relatively broad boundaries for those. Questions about this? It might take a little time for you to run the code, play with the code, dig into the code, for you to really get to grips with it. That's okay. Again, I can do my graph viz thing. And so here I have, these look kind of strange because of the way I've defined them in the PyMC3 model, but these are my A's and B's. They have priors over them, hyperpriors. These are the hyperpriors out here. And here's my likelihood. Okay. If we were to run that, I think that there's maybe a mistake, a bug, but I think it still works. You'll notice that this, I'm not sure if we ran the version before, the non-hierarchical version, but this takes very little time. It's really fast. It's amazing. I'm definitely using PyMC3 again after this week. I'm so glad I learned it. Okay. While that's running, here's one I made earlier. So this is the posterior distribution over the intercept A for that first line again, the same line that we looked at earlier. So this is just a diagnostic plot. I can't make a corner plot for that many parameters. Corner definitely wouldn't like it. It's too big. So instead of it's easier to just pull out individual parameters and plot posteriors. But here you can see that, so this is the true and inferred value of A and B for that first line. And you can see that's still not perfect. The inferred value is not the same as the true value, but it is within 1 sigma still. And it's better than it was before. So here is the data again. The true is orange, the non-hierarchical is red, and the hierarchical is green. So we've used all of the lines to learn about the one line. And that works because they're all drawn from the same underlying distribution, the same prior. Okay, I think we need to go and do a photograph, right? Okay. So after that, here are the population parameters. Mu A, mu B, sigma A, sigma B, the true values are the orange lines. And you can see that we're doing a pretty nice job constraining mu A and mu B. We're not doing so well constraining sigma A and sigma B. And that is just because we have a lot of noise in our observations. There's quite a lot of degeneracy between within sigma A and sigma B. And if we were to reduce the error bars on our lines, we'd constrain these parameters much better. And you feel free to play around with that if you want to see how sigma A and sigma B respond to changes in the models. Part of you having this notebook on your laptop is so that you can go back and play it, change things, and tweak it. Okay, then after that, all that's left in this notebook is the same thing, but in MC. So the model, the likelihood, the prior, the posterior, for a single line in MC. When we come back after the break, if you want, you can work on how to turn this hierarchical. If you really like MC and you want to learn about how to do this in MC, that could be something fun to try. But bear in mind that you probably won't be able to run it on so many parameters. But you could tweak the numbers, you could change the number of lines, you could reduce the number of parameters to something more manageable. But we have another exercise as well to do after the break, so this is just optional. Okay.
All right, so are there any questions for Ruth?
So in the example that you gave about the, like, say, measuring in 4 different spectral orders, the RV, you had said that, like, often what people will do is measure it in the 4 of them and then take the mean. And the more principled way to do it is to infer from all of them at the same time. Is that I guess my question is, if you were to end up deciding that they were drawn from the same distribution and that distribution was a normal with a mean and standard deviation, would taking the mean of the 4 of them, or the 4 separate measurements, give you the same thing? Or can it be different?
So, okay, so there are 2 things. So one of the reasons why taking the mean and standard deviation of the posterior results is not the correct thing to do is because it's a posterior and you're not supposed to multiply posteriors because you're then folding in the prior many times. You can multiply likelihoods, but not posterior. So what you could do if you had likelihood samples from each RV measurement individually, rather than posterior samples, you had likelihood samples, then you could sum them, take the mean, divide by the prior, or multiply by the prior, and that would be okay. But what you're doing in that case is removing any covariance. So the full thing would give you the covariance between the individual RVs and the population parameters. It might not be that that covariance is significant, in which case it's fine to not do it hierarchically. If it does become important, then you'd get a different answer. That's a subtle point, so we can talk about it more if that wasn't clear.
I guess if both a non-hierarchical model and the hierarchical version of it are correct, and say if they both converge in the MCMC sampling, would the hierarchical version do at least as well as the non-hierarchical version?
Yeah, I think if your sampler is run to convergence or to infinity, yes, the hierarchical version would do as well as the non-hierarchical version, but probably better. But given infinite computation time, that's you can do that. But the decisions about pragmatism are important because we have to weigh up the pros and cons of how much increased precision do we get per hour of computation time, and sometimes that maths doesn't work out to be in your favor. But yes, the hierarchical version will, I think, always do as well or better than the non-hierarchical version given infinite computation time, as long as your model is correct.
Is there any rule of thumb, like how many data points are suitable for how many hierarchical hyperparameters or something?
I think it's very dependent on the situation. I'm not sure that there's a rule of thumb for when it's okay to go hierarchical. I mean, you can go hierarchical with just two families of measurements, and people often do. Yes.
If I only have 30 observations, I will intentionally say, oh, I should not use it to infer. But if I have hundreds, will it be suitable for do that way?
Again, it really depends so much on the specific problem. Sometimes going hierarchical can help you if you have small amounts of data, but sometimes it can hurt. So if you feel like you have a good understanding of what the prior is, like from physics what the prior should be, and you have a small number of data points, you can do the non-hierarchical thing and it might be better. But if you don't know what the priors are and you want to infer them, if you go hierarchical, you might actually get a weaker constraint on the parameters of interest, but it might be more accurate. It might be less precise, but more accurate, because you decided you don't know what the prior is. You want to infer it. And so everything will be more weakly constrained, but more correct. If you choose the wrong prior, then you're going to get inaccurate results. Does that help?
Yeah, I guess.
It's hard for me to say. I'm not sure that there's necessarily a rule of thumb for the number of data points. Yeah.
Maybe one point. Will it be suspicious if you see somebody saying, "Oh, I have 100 data and now I use it to infer constraint hyperparameters"? Will people have this kind of experience? No.
I don't think so. I mean, yeah. As long as if it seems reasonable, the uncertainty in all of their parameters seem reasonable, but I don't really know what reasonable is. But otherwise, maybe they've done something wrong. But yeah, that you can still go hierarchical with a small amount of data, I think. Yeah.